Okay, now let me go over these notions over an example. Particularly, we will consider a lattice example and how can we talk about its strength, its determinant, and so on. And this example will be also important for us because function field lattices will be the substructure, as will we see in the following lectures. And in this example, we will consider a lattice, which is denoted by a n-1, which is defined as the set of vectors with integer entries, such that sum of the entries is exactly equal to 0. So by abusing the notation, I call it the hyperplane lattice because we also have kind of hyperplane structures, but this is just the abuse of the notation or abuse of terminology. And if we have such a structure, we can easily verify that this is Z module, right? This is obvious by the definition. So it provides, like, it satisfies the module structure over Z. And here we can note that the vectors bi's, which start with 1 and -1, is positioned at the ith coordinate. Forms a basis for an-1, because any vector inside of it can be written as like xi's, bi's. And if it is the case, we have n, and we can also verify that this bi's, when I runs through from 2 to n, they are linearly independent over R, so the rank of this lattice is indeed n-1. And we can consider basis matrix. This is going to be n-1 times n matrix. And B times B transpose can be computed as the matrices with entries 2 to 1. This is going to be symmetric matrix with diagonal entries 2, and the other entries are 1. So the determinant of this lattice can be easily computed by taking the determinant of B times B square and its square root. So in this case, it is going to be square root of n. So this is n-1 times n-1 size matrix. And like the minimum vectors of a n-1 is in the form of plus minus with the 0 entries, but we also have 1 and -1 entries, plus 1 and -1 entries. And the minimum distance in this case is going to be square root of 2. Because any other vector inside of this structure will have length at the square root of 2. And if we count the number of SL by using the combinatorics, we can compute the kissing numbers as 2 times n choose of 2. So here in this case, we want to locate plus and -1 in the n tuples. So this denotes this choice, and from the plus minus 1, we get twice of this quantity. And actually, we can also talk about if it is well-rounded. We can decide if it is well-rounded or not. So just look at the definition of the well-roundedness. If SL contains K linearly independent vector over R, we say that this is well-rounded. But as we have seen, these BIs forms a kind of basis for the lattice structure, and these, like the length of these vectors, are squared of 2. So this is exactly equal to the minimum distance of the lattices, our lattice. And indeed, in this S of L, we have n-1 linearly independent vectors, because I mean, all basis vectors are in SL. So an-1, this hyperplane lattice, is well-rounded. So in the second part of the lecture, now we are ready to consider function field lattices. And for the basic construction, for the basic setting, we always work with a function field over a finite field with of genus G. And for this construction, like as I mentioned in the last exercise class, when we considered the construction of algebraic geometric cos, like in the setting, like similarly in the setting, we will fix an n tuple. In the literature, like these are the n distinct places. And in the literature, in general, this set of places, this n tuples, is considered with the rational places, but we can talk about general construction. So in the beginning, we are not going to worry about their degree. And a kind of like the order will be important, but by the use of notation, we can say that this curly P is a subset of the set of places. And as mentioned, like in general, it will be, it contains like the rational places, but we can talk about the general construction. And in one of the exercise class, in one of the exercise questions, we have considered the set of curly P star, which contains functions whose supports, so their poles and zeros, is a subset of this finite set. And like when you show that this OP star is a multiplicative group, it was quite nice to see that you all, like every student, show that this is an anonymity set, but in general you show that by observing the non-zero constants are like the set of the non-zero constants is a subset of OP star. But with the last exercise, with one of the questions in the last homework, you can see that like if we have a place, if we fix two places in this curly P, let me denote it Pi and Pj in the curly P, and with degrees di and dj. And if we recall that H denotes the class numbers, we can see that the divisors di minus pj h times di times pj minus dj times pi is a principal divisor. Indeed, this is a degree 0 divisor, right? Because like the degree of this divisor is 0, so when we add it h many times, again we get degree 0. But this is principal divisor and it's not supposed to be constant. And the reason of that, like this is coming from the group theory. If this is a degree 0 divisor, and if the order of our group is H, so by using the group theory, if we have a group, let G be a group of order G, and for every element, let me note it by E, sorry for this. G to the E should be, let's say X, G to the X should be identity. So by using this fact, indeed, we can see that this divisor is a principal divisor. So this OP star also contains some transcendental functions. So it can also contain some principal divisors. So there can be also some transcendental functions inside of there. And by using this multiplicative structure, multi-abelian group structure, we can consider a group homomorphism from O curly P star to R to the N by mapping every function inside of it to the n tuples, and this n tuples is defined in terms of valuation of this transcendental or this function z at P1 times degree of P1 up to the nth entry's valuation of z at Pn times degree Pn. So one of the exercises will be to verify that phi sub p is phi of p as a group homomorphism. So here note that we have the multiplicative notion, and here we consider the group structure with respect to addition. And what is called the function field lattice is the image of this map phi p. So delta p is called the function field lattice associated with the function field f and given n tuple curly p. So the natural question is that, so what kind of properties we do have for the structure, or maybe the simple question I can ask that is, what is the kernel of this map, and what can we say about the total image? Can we provide something about its rank, its minimum distance, and so on? And these will be the notions I will try to explain in the following records.